All right, so if you take a look, like I said, this is a section. It's section 2.5 in your book. But what we are doing, we're talking about what's called the fundamental theorem of algebra. You've already done this. You learned it last year. We just don't use the name very often. But for the most part, what we're doing is we're now putting all this stuff together. Okay, we're taking all of the factoring, finding the zeros, what's the shape of the graph, the end behavior, and we're kind of putting all of that stuff that we've talked about together. So here is what the actual fundamental theorem of algebra says. That, like I said, you already know. Right here. It says that for any nth degree polynomial, you have n number of zeros. So a fourth degree polynomial has 4 zeros. Fifth degree would have 5 zeros. And that could be real and imaginary. Doesn't mean that it has to be all real zeros. You might have some imaginary ones. You haven't had that yet in this class because we stayed with the real numbers in the first part of this. And then we just yesterday, we introduced imaginary ideas. Now going forward, you could have some that have some real and some imaginary answers. Okay? But that's all the fundamental theorem of algebra says. Whatever degree, you've got that many zeros total. And if you have any repeated, like double roots, each one of those counts as a single root as well. Okay? So if 2 was a double root, you'd have a 2 and then another 2. Okay? That's 2 zeros, not 1, even though it's one number. And then there's something I need to add in today that connects what we talked about yesterday. And that is, when you're finding zeros, complex zeros always come in pairs. Always conjugate pairs. So if you are finding zeros and you do get a complex number as an answer, let's say you get 2 plus 3i, that means right away you automatically know 2 minus 3i is also a 0. They always come in pairs. Okay? And you haven't had to do that yet because we haven't been finding complex zeros yet. So 2 things to keep in mind as you work your way through. Total number of zeros and complex roots always come in pairs. So if you know one, you automatically know a second one. And you'll see that today in some of the examples. All right. So here's example number 1. Here's where we're going to start putting this all together. So we've got a 4th degree polynomial. We've got a quartic polynomial. I want to find the zeros, okay? And then from there we'll also add in, I didn't put this in the directions, but at the very end then we'll go through and we'll actually sketch the graph based on what we see, based on the equation, based on the zeros. We'll put it all together so that we have it. All right. So if we're going to find the zeros, what we've used so far, we've got factoring, we've got quadratic formula, if it's quadratic, okay, which it's not, so we're not going to use that. We've got synthetic division, we've got long division. Those are basically your methods of finding zeros. Okay? So really, for the most part, there's 3 on this one that could happen. You could factor, synthetic, or long division. What's the problem with synthetic or long division right now? We've got nothing to start with. Okay, somebody had asked last week, I think that was, no, maybe not, okay. So somebody asked last week, well, what do we do if you don't have something to start with? We'll talk about that in the next example, okay? And we'll get something. But right now, you don't have a factor to use for long division or a 0 to use for synthetic division, which means right now the only method we have is factoring. I'm hoping when you look at this, you see a difference of squares, because that's what this is. Okay? I'm hoping you see a difference of squares when you look at this. So let's factor it as such. So what's the first thing we're squaring? In order to get x to the 4th, what do you square? X squared. So there's the first part in each one of your factors. What do we square to get 625? 25. There's the second part of each factor. And because this is a difference of squares, we know the 2 middle terms are going to cancel out. In order for that to do it, we need 1 minus and 1 plus sign. We need opposite signs. So we factored that. Now we take a look at those factors and say, can we keep going? Can I keep factoring? First one, can I keep going? Yep, there's another difference of squares. Let's factor again. So that'll be x plus 5 and x minus 5. What about the second factor? It's not a difference of squares because we have a plus sign. So what do I do with that? Yeah, you can still solve. There's still just one variable in that problem. So zero product property. Set it equal to 0. X squared plus 25 equals 0. I'm going to come back to that. I'm going to finish up the first ones. One of my zeros is negative 5. Second zero is positive 5. And then this is where we're going to get, we know we've got a fourth degree, so I know I've got a total of 4 zeros. I found 2 of them. The other 2 are going to come from here. So let's subtract the 25 over. Take the square root of both sides, which, remember, plus or minus, when you take the square root, that's why we have 2 of them. Plus or minus what? 5i. Okay. Square root of negative 25 is 5i. There's your last 2 zeros. So in this case, we knew we had 4 zeros to begin with. That's the fundamental theorem of algebra. There's your 4 zeros. 2 of them are real. 2 of them are imaginary. Now let's put this together. I didn't ask you to, but let's put it together anyway so you can understand where this is going. Okay? So let's take a look. Let's put it on the graph. There's 2 of my zeros. What shape is this graph going to look like? It's going to be a W. You know it's, again, fourth degree, W or M. Because it's a positive x to the fourth, it's opening up. That's what makes it a W. I put the real zeros on the x-axis. Where do the imaginary zeros go? It's kind of a trick question. They don't go anywhere. The only zeros you ever see on a graph are real ones. You don't put the imaginary zeros anywhere. Okay? And so if I know this is going to be a W shape that's kind of opening up, and it's got to go through those zeros, the sketch then you could come up with would look something like this. Some version of that. There's the W shape with only 2 real zeros. Going through the x-axis twice. The other zeros are imaginary, which I have, but you don't see them on the actual graph. Okay. Questions on that? Like I said, this is where we're starting to put this together. Shape of the graph. Finding the zeros. Now we've got some imaginary ones. We talked about factoring. We talked about synthetic and long division. That'll come into play here shortly, but not yet. All right, let's go to example 2. Different reason why this one is in here. Again, let's say we want to factor. Let's say we want to find the zeros of this function. So that eventually you could go through and actually sketch the graph if we needed to. Again, if you think of the 4 method of finding zeros, we've got factoring, which we'll talk about in a second. Quadratic formula, that's out because it's not quadratic. Synthetic or long division, which are currently also out because I have nothing to work with. So let's start with factoring. When you see this, what should you be thinking of? Grouping, because there's 4 terms. Okay, now let's take a look before you do grouping. If I group the first 2 together and factor out an x squared, what would I get in parentheses? You'd get x plus 11. Remember, grouping only works if you can get the same stuff in the parentheses. Can I get an x plus 11 here? Grouping's not going to work. So it's the only method you currently have to factor this, and unfortunately it's not going to work. Can't use quadratic formula because it's not quadratic, which now we come back to synthetic or long division. I didn't give you anything on this one. So this is where, on your homework, okay, in class, we would type this into our calculator and find a 0. So I have something to work with, and I'll do that so you can see it. Okay? If this was on the assessment coming up on Friday, we would either give you the graph or we'd give you the 0. Okay? So that way you have something to work with. So you wouldn't have to go through the process of finding it on your graphing calculator. You will have it otherwise. Okay? But if we do that real quickly, let me take you to the graphing calculator so you can see it. you got a couple of methods. Number one is put the equation into your y equals. The x cubed plus 11x squared plus 39x plus 29. And then from there, we already talked about this, so hopefully this is just a revisit. We go into the calculate menu. So we hit second and trace. This comes up, and I'm looking for a 0. Okay, I'm looking for a 0. So I would choose number 2. And then here's the point where, again, they talk about left bounds and right bounds. We did it with maximum and minimums before. Now you're just bounding the 0. One thing I want you to take a look at is, we said this is a cubic function, which obviously you cannot see the whole thing. But if you understand what you're trying to do, okay, we're starting with a cubic function. Our goal, anytime we do synthetic or long division, is to get that down to a quadratic. Because if I can get it down to a quadratic, then I can either factor or do the quadratic formula. I have tools to use once we get to a quadratic. So really, if I'm already at a cubic, I only need 1 0. I can then do the synthetic division, and I'll have the other quadratic factor to work with. So even though I can't see the whole shape of this, doesn't matter. All I really need is that 0 right there. So if we find it, I'm going to go to the left of the 0, a little bit more, hit enter. Then we go to the right of the 0, hit enter, and then just make sure you come back somewhere in between your two boundary points that you just created, and hit enter, and we find out that it's at -1, okay, which you can kind of pull off the graph anyway, but we find out that -1 is one of the zeros. And now you do have something to work with in the problem. Okay? Now you do have something to work with. So let me go back to that. So step number 1, now I know x equals -1 is a 0, which means now I can do synthetic division or long division, whichever one you prefer. Okay? By the way, if you're going to do synthetic division, what would I use? -1, the 0. If I'm going to do long division, what would I use? X plus 1. You use the factor. Okay? I don't care which way you do it. The one thing I'll give you a heads up on as a recommendation, a lot of times when you get to a test or an assessment or something along those lines, you're a little bit pressed for time. Which way would be quicker? Synthetic. Okay? Which is why we kind of showed you both. Synthetic division is a quicker method to get to the same end result. So if we take -1, let's do it with synthetic. Take your coefficients. Remember, if any of them are missing, make sure you fill them in with zeros. So we've got 1, 11, 39, and 29. Okay, we don't have any missing, so I don't have to fill any zeros. And work your way through the process of synthetic division. Bring the 1 down. Multiply, I get -1. Add, we get 10. Multiply by the -1, I get -10. Add, we get 29. Multiply by the -1. Add, I get 0. Quick question. Why should it make complete sense that I got a remainder of 0? Because you knew it was a 0 ahead of time. You took it off the graph. You know if you don't get 0, you did something wrong. Okay? Either you did something wrong on the graph or you did something wrong in your synthetic division. That's confirming that, yep, -1, it's a 0. We got a remainder. Okay? We have a remainder of 0, excuse me. So now, here's where we can put this together. Remember, synthetic division is a form of factoring. What are my factors? Since -1 was a 0, that means x plus 1 was the first factor. What's my second factor? It's right here. Okay, it's right below. That's one of the reasons for the synthetic division. You went from a cubic function. These numbers down here below the line are now your coefficients of a quadratic. 1x squared plus 10x plus 29. And now I still need to find the final zeros. I'm not going to, but we need to. If you look at this factor, can I factor that? Sometimes you will be able to, by the way, but this one's not factorable. Which means, Preston, I heard you say it. At this point, you'd have to do the quadratic formula to find those last two zeros. which might be real, they might be imaginary. Depends on what you get in the quadratic formula. Okay? But the idea here is, now you go to the quadratic formula and find your last two zeros. Okay? Whole point of synthetic or long division is to get to a quadratic factor, so that I then can either factor or do the long division, or do the quadratic formula, excuse me. Okay? Making sense? Getting the idea? I'm going to leave it because I think you can handle the quadratic formula. So I'm going to leave it alone on that one. All right, let me give you one more type of example here. I've got a couple examples after this, but this is going to then lead to the last concept. So just like last week, we started with, here's these equations, let's find the zeros. Then we said, let's go in reverse. Here's the zeros, let's find the equation, let's see where they came from. Same thing here. Now I'm telling you, here's your zeros. What was the polynomial we came from? Okay, where did this come from? First question, what degree did this come from? 3 zeros means we have third degree. Notice, conjugates always come in pairs. If 3i is one of them, then negative 3i is definitely going to be another zero. And we can do this the same way we did last week. I can take the zeros and turn them into factors. Okay, so 4, we've got x minus 4. 3i, we've got x minus 3i. And negative 3i, we've got x plus 3i. Okay, we didn't have imaginary factors before. Okay, but now we will. This one's not too bad though, because of the fact that I didn't give you a full complex number. If I would have given you like 2 plus 3i and 2 minus 3i, then it gets a lot messier. Now you're back to, remember those problems last week that had the square roots in it, where we ended up multiplying it all out and had this huge line of terms? That's what it would have been if this was like 2 plus 3i or 2 minus 3i. But because it's just the imaginary part, it's not as bad. I am going to start right here with these two. Let's multiply those out and see what we get. So let's bring the x minus 4 down. I'm not going to do anything with that yet. If we multiply this out, remember the shortcut I talked about in the homework? Same shortcut applies. This is a difference of squares. So I already know that the two middle terms are going to cancel out. So all I'm going to focus on is the first term and the last term. Because I already know when you've got a difference of squares that those middle terms are gone. So x times x, I know I'm going to get an x squared. Negative 3i and positive 3i. I end up with a negative 9i squared. And not that you couldn't multiply out the other terms. I just don't need to because they're going to cancel out anyway. Okay, if you understand that ahead of time. Which means, by the way, what's my second factor? Let's get rid of that I squared. X squared plus 9 is your second factor. Because I squared equals negative 1. And once again, I'm not done, but I'm going to be done. Now if I wanted, we said this would come from a cubic function. Now you would multiply this out. You'd FOIL it out from there to get your cubic function. Okay? So you would keep going to get x cubed, whatever. Okay? What I want you to notice is this, and this is what this was leading to. This was the point of this problem. When we multiplied complex conjugates here, notice we actually ended up with a pretty decent quadratic factor. Pretty nice one. That actually always happens. Okay? You end up with a quadratic factor that's actually not too bad, which leads us to the sum product rule, okay? Which is actually a nice little shortcut that you can use. Okay? The sum product rule. Right back. I gotta grab Mr. Nazi. By the way, I'll be gone tomorrow. I have a meeting in the middle of the day, and Mr. Natsky's subbing for me. That's why he's coming over to hear this rule.
You're stuck at me tomorrow. No choice. You're stuck.
I'll be, like I said, so I'll be gone middle of the day for 4th and my 5-6, but Mr. Natsky will be here. So sum product rule. Here's what it says. Anytime you have complex zeros and their conjugates. Okay. So for example, I told you before on the last one, if this would have been like 2 plus 3i and 2 minus 3i, then you would have had to have something like this. And you would have taken that and done all the multiplication. And again, that's what I was talking about last week, where we did all those square roots that all the terms multiply out and it gets kind of messy. This is a shortcut, so you don't have to do this. Okay? First off, if we wrote them as factors, x minus whatever, like we just did, okay, when you multiply that out, you do get a quadratic. Notice, by the way, that I didn't put an a value in there. Anybody tell me why? What does a equal? Since we already know it's x minus, we know a is 1, so I don't really care about the a value. I know I'm going to get x squared. What I care about is, what's the b and the c value? If I can put numbers in those spots, I have the quadratic factor. And if you think about in general, here's where the sum product rule comes from. Normally, if you were going to factor something in this form, we've talked before about what are the factors of the constant that then add to the middle term? Sum product. Product is what multiplies to give you c and what adds to give you b. It's the same concept. It's coming from the same place. Here's what you do. Add the real parts. If you take your two complex numbers and you add the real parts together and use the opposite sign, that gives you b. Okay. And again, I've got an example coming up here in just a second. You'll see. Add the real parts together and use the opposite sign gives you b. And if you just multiply the complex conjugates out, like we've been doing on a couple of different examples, it gives you the c value. Multiply to c and add to b, just like when you factor. Only difference is we got to use the opposite sign. And I'll give, like I said, I'll give you an example here in a second. All right, let's take a look. So here's the idea. I'm going to do it first. I'm not going to do it, but I'm going to set it up the way that you don't want to do, and then we'll do it the way that you do. We'll show you the shortcut version. So this is the same idea as the example before. I'm given the zeros. I could write them as factors, multiply them all out. If I did that, we would have x minus 6 as our first factor. We would have x plus 5 minus 2i as our second factor. And we would have x plus 5 plus 2i as our last factor. And you would have to go through in order to get your quadratic factor and multiply and do all the distributing and work your way through all of that. Here's what we can do otherwise. Here's how we can use the sum product rule. I'm going to leave the x minus 6 alone for now. We said that based on the sum product rule, we already know the first part's going to be x squared, okay, because it's in x minus form. So we already know we're going to have x squared. I'm going to try to find the b value. Well, the b value says add the real numbers and use the opposite sign. In this case, here's the real part, negative 5 and negative 5. Add them together, you get negative 10. Change the sign, plus 10x. All that's coming from is add the real parts of your complex numbers and change the sign. Okay, and we'll talk about it again in a second. To find the last part, the constant, all you have to do is multiply out the complex conjugates, which, like I said, we've been doing that. If I'm going to multiply these out, it's just a difference of squares, which means I don't care about the middle terms. We just care about the first and the last term. Negative 5 times negative 5, 25. Positive 2i times negative 2i, negative 4i squared. Which, when I simplify that, what will I get? I'll get plus 4, which gives me 29. Okay? Remember, I squared is negative 1, so this is really a plus 4 right here.
You said it so
Okay.
confidently in that part.
You were there. You were there. Plus 29. And now, so that I did not have to go through and actually take these two giant factors and multiply them all out, there's kind of the shortcut version to get there. Okay. Add the real parts and take the opposite. Multiply out to get your C value. Okay. Now, let me ask you this. I'm not done, but I'm going to be done. Because what's the one thing left to do if I wanted to? Yeah. You now would have to go through and take the x and distribute, take the negative 6 and distribute, and get your, again, get your cubic function. Okay, so we're not quite done, but it's a much quicker method than having to multiply all of this stuff out and then still have to do that. Okay, it's a little bit of a shortcut. Okay. Some product rule.
All right. I just didn't remember which things you summed and which thing you
Yeah.
producted. So, yep.
Let's do it one more time. I got one final example here for you.
See you guys tomorrow.
All right, last example. This will be about as difficult as it gets. What is that? Maybe. Yeah, you're on the right track, yep. All right, let's take a look. This is about as hard as this will get. So notice, I asked you if 5 plus 2i is a 0 of that cubic function, or cubic polynomial. If the answer is yes, then I want to find all three of the zeros. Okay? What's your first thought on how to work your way through this? What do you think, Aiden? Okay. So if 5 plus 2i is a 0, we know we also have 5 minus 2i. So if I know 1, I actually know 2, which really only leaves one more 0 to find if that's a 0. Okay, so you're on the right track there. That's going to come into play. What if I asked you this? Let's simplify this for a second to get the concept. What if I asked you, is 5 a 0? What would you do? What would you do? I think somebody said it. Synthetic division, right? Probably. You take 5 and check to see if you get a remainder of 0. If you do, you know it's a factor. So you could, I'm not going to say that it's not possible. You could use complex numbers to do synthetic division. It gets really messy really quickly. So we're not going to do it that way. Okay? But it is possible to do synthetic division with complex numbers. What we're going to do instead is kind of what Aiden had talked about. If I know that 5 plus 2i is a 0, then that means 5 minus 2i would also be a 0. And I'm going to do what we just did. I'm going to take those, and let's assume that those were factors. Let's come up with, if I were going to multiply this back out, let's get a quadratic factor using our sum product rule. So that means we would have x squared. To find the b value, what do we do according to the sum product rule? Add the real parts and change the sign. So we've got plus 10. Change the sign. This becomes a minus 10x. Okay. Yeah, Devin?
Wouldn't it be a plus 10x because if you were to make those into factors, it would be minus 5 plus?
So good question. When you're doing the sum product rule, you're using the zeros, not the factors. Okay, good question on clarifying that. So when you do that sum product rule, you're not looking at it as from the factors form. You're looking at it from the actual zeros. Okay? So you're right, though, yes. If I wrote them as factors, it would actually be x minus 5. You want to look at them as zeros. Okay? So now, to find that final c value, I need to multiply these two out. Which, by the way, we basically just did that. The only difference is we have a positive 5. We change the signs again. So if we multiply this out, we would get 25 minus 4i squared, still giving you 29. Okay? 29, good, Flynn. Well done. Got it. Now let me ask you a question. So I did some work. I still haven't answered the question, though, whether it's a factor. How can I now that I have this quadratic, how could I find if this is a factor? Here comes the long division. This is why last week on Friday when I told you there are times where you have to do long division. Here it is. Okay? If these are zeros, this would be the factor where they came from. Now I can check to see, does this actually go into this cubic function? In order to find out, we got to do long division. I will tell you this though, even though it looks super complicated, because it's complicated, it's easier. It is. Watch. Just watch. It's going to be easier than it looks. Here it comes. Let's do some long division. By the way, how am I going to know if this is a factor? Remainder of 0 is what I'm looking for. Okay? I'm looking to see, does this give me a remainder of 0? And then I can answer the question from there. All right, I told you it looks messy. Don't forget if you need zeros on anything, we don't. But if you would, make sure you put those zeros in. What's the first thing going in our quotient? Our answer? X. Yeah. X squared times what gives me x cubed? X. So we take that and multiply it through our divisor here. X times x squared is x cubed. Times negative 10x gives me negative 10x squared. And plus 29x. And subtract. Okay. Or add the opposite. I'm going to add the opposite to clean it up a little bit. So negative, positive, negative. Now I can just combine like terms. X cubes go away. I end up with a positive 3x squared. I end up with a negative 30x. And then I bring down the plus 87. And we go again. What's the next part of the quotient? X squared times what gives you 3x squared? 3. So plus 3. We multiply it through. We get 3x squared. We get minus 30x. We get plus 87. And when I subtract, I get a remainder of 0. So let me ask you a question. Let's go back to the problem. Is 5 plus 2i a 0?
Yes.
There's 0 number 1. Is 5 minus 2i a 0? Yep, there's 0 number 2. What's my last 0? There's your other factor right there, which means x equals negative 3 is your final factor. This is the one time where you have to use some long division in order to work your way through the problem. Okay? I got a worksheet for you today, which is just a couple of quick things I need to mention.